How you guys doing? This is a video to show you the ways that bacteria can fix or grow their cell walls. In addition to this, it is how um, antibiotics, certain kinds of antibiotics called beta-lactam antibiotics, can destroy bacteria, basically how the antibiotics can do their job. And the third part of this is how certain bacteria can become resistant to the effects of the antibiotics. So if we take a look here, here's the cell membrane of the bacteria, and we also see here have the cell wall. So we can see here that these are the layers of the cell wall, the peptidoglycan layers. Excuse me. And each of these layers has sort of this little thingy hanging down, and basically this is just a little piece of protein. And it needs to be kind of stapled together, for lack of a better term. And so this enzyme right here is the one that does it. This is called transpeptidase, otherwise known as penicillin binding protein. And so normally what you'll see this thing doing here is that it will be kind of stapling together these little cross bridges. And there it goes, to kind of make this stronger. And so if we back up the view a little bit, we'll see that there's this enzyme, transpeptidase, and it's kind of stapling together, there it goes, all of the different areas of the bridges between the peptidoglycan, which makes it much stronger. As you can imagine, with a gram-positive organism, there's probably thousands or hundreds, if not thousands of layers, probably hundreds, of these particular peptidoglycan layers that are cross-linked by these bridges right here. This enzyme, again, is called transpeptidase or penicillin binding protein, and its job is to staple together these different layers. That's normally what happens. The bacteria has this enzyme. So what happens when we introduce an antibiotic? This is a pictorial version of a particular type of antibiotic called a beta-lactam antibiotic, and it's called that because it's in the shape of a beta-lactam ring. Most of the illin antibiotics that you know of, ampicillin, penicillin, methicillin, and a few others, those are your beta-lactam antibiotics, and they're in this shape. And basically what happens is when the penicillin or any of the beta-lactam antibiotics are introduced to the actual cell, you're going to see that they have a pretty good conformational change here, in the sense that they are able to, I shouldn't say conformational change, they're able to bind to a particular enzyme. Boop, there you go. And if we stop the video right here, we see that this is the penicillin, or the beta-lactam antibiotic, and this is the penicillin binding protein, or the transpeptidase, of the actual bacteria. So remember, this thing's job, the green thing's job, is to staple together the finishing touches, per se, of the creation or maintenance or fixing of the cell wall. So if we watch what happens, we see here that the penicillin binds to the penicillin binding protein, or transpeptidase, and so now what can't happen is the cell cannot hook together all of those different layers. And so what happens over time, because of osmotic pressure, basically the cell bursts. And so that is a quick story of how beta-lactam antibiotics, and remember there are way other kinds of antibiotics, but that's basically how they work to help cure patients. So basically, what are some ways that the bacteria can become susceptible, or I should say, really what I should say is, how can the bacteria become resistant to the effects of these beta-lactam antibiotics? What are some of the mechanisms behind it? And so if we take a look here, we can see that one potential way could just be genetic variation, that over time, over the many different potential mutations that these bacteria could have, they potentially, or some of the individuals, could produce altered penicillin binding proteins just by sheer mutation. And so what could happen at that point is that these altered penicillin binding proteins would still be able to do their job. And what I mean by doing their job is they would still be able to cross-link the peptidoglycan, but the penicillin over here can't fit into the active site of this enzyme. So therefore, this cell is going to be resistant to the effect of any of these antibiotics. There's also another way that these bacteria could have some resistance against this particular type of antibiotic, and that is basically by the production of a new enzyme. And so if we take a look here, some bacteria, as you know already, can do conjugation, where they can basically make a copy of some DNA in a plasmid and give that particular gene to another bacteria. In this case, there are genes that exist to produce these types of enzymes, and these are called beta-lactamases. And so, as you can imagine, they work on beta-lactam antibiotics. And so, how do they work? As you're going to see here, in the presence of the let me fast forward a little bit here. There we go. In the presence of the antibiotics, there's your penicillin binding protein. Okay, so here's all three players. Here's our normal penicillin binding protein, whose job is to cut or to staple together the cell wall. Here is your antibiotic that normally would be fitting into this thing, but some bugs produce an enzyme called beta-lactamase, and that's this. And as we let the video go, you're going to see what's going to happen. The beta-lactamase enzyme basically breaks the bond of the penicillin, and so the penicillin is now basically useless, and so now this bacteria can go about its business fixing its cell walls and not have to worry about the presence of penicillin. So that's one particular mechanism that we see, and there's a few more, but in terms of your exam, a basic understanding of bacterial resistance and beta-lactam antibiotics is of concern. And MRSA, some cases of MRSA, methicillin-resistant Staph aureus, have been shown to have this particular type of mutation as well as some of the others. So hopefully this helped.